Today we're going to take a look at solving systems of equations in another method. We're going to learn the method of elimination and find out when it is helpful to use that method for solving a system of equations. We've talked about graphing and we've talked about substitution. So today we'll look at the elimination method. So elimination is helpful because the idea is we want to eliminate one of the variables. In our first example, we have an x and a y in our system of equations. If we can eliminate one of those variables, that'll leave us with the other variable that we can solve for. And then once we figure out what that variable is, we can substitute it in and figure out what the other coordinate is. So in our first instance, we notice that the y's are similar, they're opposites. So if we can just combine both of those equations, we can eliminate those y variables. So if we combine them all together, so if I add the 4x and the negative 2x, that combines to give me 2x. The negative 3y and the 3y cancel each other out. And when I combine 5 and negative 7, I get negative 2. So I'm left with an equation that says 2x equals negative 2. If I solve for x, I get x equal to negative 1. So if x is negative 1, I can substitute it into either equation and solve to figure out what y equals. So negative 4 minus 3y is 5. I can add 4 to both sides. So negative 3y is 9. Divide by negative 3. Y is negative 3. So my coordinate is negative 1, negative 3. So the idea with elimination is we want to be able to pick out a variable that we can cancel out and eliminate, whether we add or subtract the two equations. You'll notice in the second system of equations, 7x and the 7x are the same. So in order to eliminate those, we need to subtract the two equations. So 7x minus 7x, those cancel out. Negative 2y minus negative 3y gives me a positive 1y. And 5 minus 4 is 1. So y is 1. Substitute back in. Just choosing the top equation just for convenience. It doesn't matter which one I choose. 7x minus 2 equals 5. Add 2 to both sides, so 7x equals 7. Divide by 7x equals 1. So my final coordinate would be 1, 1, if I were to graph it. So this method becomes easier than substitution because we don't have to get the variable all by itself and then substitute it in. And it's easier than perhaps graphing because we don't have to get the equation into slope-intercept form and graph it or find the intercepts. We can simply just eliminate variables. In this instance, we'll notice it might be hard to eliminate variables because they're not all lined up very well. So we want to line them all up first, and then we can determine which ones we can eliminate. So I'm going to subtract 4x from both sides in the first equation. And that'll leave me with negative 4x and a positive 5y equals a positive 6. And I'll line the other one up below it, since that one's all lined up the same way. And then I look to see which variable I can eliminate. The 5y's are the same. So if they're the same, I'm going to subtract them. So I'll subtract the two equations. Negative 4x minus 2x is negative 6x. The y's will cancel out, and 6 minus 12 is negative 6. Divide by negative 6, I get x equal to 1. Plug it back in. This time I'll plug it into the second equation. So 2 plus 5y equals 12. Subtract the 2, 5y equals 10. And then divide by 5, y is 2. So my coordinate is 1, 2. Okay, why don't you try that second example and see what you get. Restart the video when you're ready. So in order to rearrange the equation, I had to get the x's and the y's to match up. So I just switched those around to make it negative 5x plus y. equals 13, and then I notice the y and the negative y are opposites, so I need to add those equations. So negative 5x plus 2x is negative 3x. The y's cancel out. 13 plus 32 is 45. Solve the x is negative 15, then I plug that back into the equation. Simplify it, and I get y equals negative 62. Now, let's take a look at what happens with some special cases. Notice if we're going to graph these, why don't you just take the time and, first of all, graph those, restart the video when you're ready to see what the graph looks like. So you may want to get those equations in slope-intercept form first of all. So notice I subtract 2x from both sides to get y equals 5 minus 2x, and y equals 1 minus 2x. So 5 is my intercept, slope of negative 2. 1 of an intercept, slope negative 2. Notice they're parallel lines, they'll never cross, there's no solution to this. So what does that look like when we eliminate? Notice that we can eliminate either the x or the y variable because they're both the same. So when I subtract now, because they're the same, so 2x minus 2x, that cancels out, y minus y cancels out, so I have nothing left on the left side of the equation. 5 minus 1 is 4. 0 does not equal 4, and we've talked about this before when we solve equations. So that means there is no solution. And just wanted to show you what that looks like when you graph it and what it looks like when you eliminate. We've eliminated the variables and it's not a true statement anymore. Let's do the same thing with these next set of equations, graph it, and restart the video when you're ready. So once I rearrange both equations into slope-intercept form, I notice that I get y equals 3 plus 2x for both equations. And it means that the lines are right on top of each other, which means I have infinitely many solutions because I have equivalent equations. So what does that look like when I eliminate? Well, when I eliminate, in this case, notice that the x's are different and the y's are different. So a step that I need to do in order to eliminate is I need to notice in order to get the y's the same, I need to double the top equation. So let's double that equation. And now I have negative 4x plus 2y equals 6. Bottom equation, I still have negative 4x plus 2y equals 6. Didn't do anything to that one. Now if I want to eliminate the y's, I'll subtract that equation. So I subtract everything. Negative 4 minus negative 4 cancels out. 2 minus 2y cancels out. Left with nothing. On the left, 6 minus 6 is nothing. 0 equals 0 is a true statement. So it means that the equations are equivalent. And I have infinitely many solutions. Okay, so that's what those two look like when we solve them algebraically. We can compare that with what they look like graphically as well. So as I mentioned before, we might need to adjust the equations first before we can eliminate. So in the first equation here, notice the x's and the y's. Which one would be easier to eliminate? Well, if I double the bottom equation, that'll make the x's the same. So if I double everything in the equation, I get 8x minus 6y equals 10. Remember, what I do to one side of the equation, I must do to the other. We'll keep the other equation the same. And now, what do we need to do? To get rid of the x's, we need to subtract them. So if you can't remember what to do, just think, how do I eliminate those? Do I add them together or subtract them? So that cancels out. Negative 5y minus a negative 6y is a positive 1y. 11 minus 10 is 1. So y is 1. Plug it back in to find x. And we get x equals 2. So 2, 1 is my ordered pair. Remember, the x always goes first. Okay, why don't you try that next example? You might need to rearrange the equation or multiply one of the equations. Restart it when you're ready to check it out. The first thing I did was I got the x's and the y's on the same side. So I added 4x to eliminate it on the right side there. And so I'm left with 4x minus 3y equals 8. And then I subtracted the 2y to get it together on the left side. So now I have x's and y's on the left and constant terms on the right. Now, if you'll notice, the 4x and the 5x, neither one goes into the other one. Same with the negative 3y and negative 2y. So here we got to be a little bit more creative. So here's where the lowest common multiples come into play that you learned back in grade school. So I'm going to take a look at the x's. Since those are positives, I'm going to work with those. You can work with the y's if you wish, but I'm going to go with the x's. So I got to think to myself, how can I make those the same? Well, I know they both go into 20. So let's make them 20. You get to do whatever you want here in math class today. So I'm going to make them 20. So I'm going to multiply everything by 5. So I get 20x minus 15y equals 40. Second equation, I get 20x minus 8y equals negative 44. Now I've got the same terms, so I'm going to subtract those. Cancels out the x terms, and I get negative 15y minus a negative 8. Gives me a negative 7y. 40 minus a negative 44 is a negative 84. Divided by negative 7y is a positive 12. Plug it back into one of the equations. I'm going to go with this original one. Negative 3 times 12 equals 8 minus 4x. Negative 36. And divide by negative 4 to get x all along. I get 11 equals x. So my final coordinate will be 11, and my y is 12. 11, 12 is the solution for that system. Now let's finish up with a word problem. Where can we apply this? So during practice, a 4-person crew team rows the rowing shell upstream, then they row the same distance downstream against the current, or with the current. The shell moves upstream at a speed of 4.3 meters per second and downstream at 4.9 meters per second. We're assuming the speed of the current is constant. So let's create some models to model this equation and find out their average speed. So let's call their speed of shell in still water. We'll call that speed in still water is x, and we'll call the speed in the current, the speed of the current, let's call that y. Okay, so for our equation, if we are going upstream, we are rowing, but we're going against the current. So we need to subtract the current speed. And we know that we end up with a speed of, when we're going upstream, what's our upstream speed? 4.3 meters per second. And when we are going downstream, we have the current at our back. In that case, we're going 4.9 meters per second. But in this case, we have our speed plus the current pushing behind us. Okay, so we've modeled that saying our speed minus the current is 4.3, our speed plus the current is 4.9. So now that we've got two equations, we need to determine how we're going to solve those. I see opposites here with my y's. So I'm going to add these two equations up. So I get 2x, the y's cancel out, and I get 4.3 plus 4.9. Gives me 9.2. Divide both sides by 2. X is 4.6. Plug that back into one of the equations. 4.6 plus y equals 4.9. Subtract 4.6. Y equals 0.3. So in order to answer our question, the speed of in still water is 4.6, where are we going, meters per second. And the speed of the current is 0.3 meters per second. So if you're able to create two equations with two of the same variables, we can eliminate one of those variables and find out what they represent, and solve that system of equations in any of the manners that you've learned, whether it's by graphing, substitution, or elimination. So just remember, when you solve by elimination, we're looking to get rid of one of these variables. You can either add two equations together or subtract them. But keep in mind you may need to multiply one or both of the equations first before you can eliminate.